Hi, I'm Ruud van der Pas. I'm a mathematician, work as a senior staff engineer in the Developer Tools organization at Sun Microsystems. I'd like to welcome you to a 7-module training series brought to you by Sun. It's called An Introduction to Parallel Programming. The trend toward multi-core and parallelization is creating demand for new skills from software developers. In this series, we'll discuss parallel programming as one of the fundamentals of application development. In Module 1, we will go over tuning for performance and the challenges brought on by today's new chip architectures. For a long time, people thought that waiting for a next processor would give them the performance boost they needed. They were just waiting and would buy the new one, and instead of tuning the application, what they would say is, well, I'll wait for the next one, and 6 months from now, my problem is gone. Well, first of all, that was never a good idea to start with, but it's less of a good idea now more than ever. And let me explain you why. Assume you have computer system A and you would like to upgrade to system B. System B has a new CPU, and that CPU is, in my model, n times faster. It could be 2 times faster, it could be 3 times faster, or maybe 50%. I also assume the memory system is somewhat faster. That's modeled through my parameter k. So k is a fairly small number, it could be 10%, 20%. Because when you upgrade your CPU, you don't upgrade your memory system, you upgrade your CPU. But you do get some benefit on the memory side as well with that CPU upgrade. Let's say I can decompose my execution time in the time that I spend in the CPU plus the time getting my data from the memory. I call that tCPU and tmemory. And I reflect those components by a factor f. F could be anything between 0 and 1. So I write my time as f times ta plus 1 minus f times ta. So what's the whole point of that? Well, if f equals 0, I want to reflect that I spend all of my time in the memory system. If f equals 1 or 100%, it means that I'm spending all of my execution time in the CPU and no time in the memory system. Both are corner cases. In real life, f is somewhere between 0 and 1. With that model, I can very easily estimate what the new time will be on my system B. Because the CPU part scaled with a factor of n, so I have to divide that time by n, and the memory part scaled by a factor of k, so I divide that time by k. That gives me a formula for the performance on system B in terms of n, k, and f. So I have 3 parameters. To make the analysis a little easier, I pin down n. I pin down n to be 2, and as is shown on the next slide, I'm showing you different performance curves for the different values of k. And I do that for a varying value of f. Again, f could be anything between 0 and 100%. That's on the horizontal axis. And the vertical axis has the speed up that we should expect. The green line corresponds to k equals 2. K equals 2 is what I call the sanity check. If both the CPU and memory are twice as fast, my performance will always be twice as good. But as I just said, that's not very likely. It's more likely that k equals 1 or maybe 10%. The 20% shown here is actually a very optimistic case. And what we see in this chart, that if I spend half of my time, 50% of my time in the memory system, then I do not get the expected 2 times performance improvement out of my application. What I see, for k, let's say being 10%, I get about 40% performance improvement. And that's of course cause for disappointment on the user side. What we also see is that only if I spend a significant amount of time in my CPU, if f equals close to 1, I get a serious performance gain from my CPU upgrade. And again, there should be no surprise, but a lot of people are because they bought that faster CPU and they're disappointed they don't get the full benefit. So by improving the performance of an application, we actually move it from left to right on this chart. And what that means is that we make it more CPU friendly. Many performance problems today go back to bad memory behavior. In my chart, that means that we're on the left side of the curve, not on the right side of the curve. And that's bad news. So the bottom line is that if I do some tuning on my application today, I will not only get better performance today, but also when I go to a faster CPU, I will see more benefit of that upgrade. In other words, it does pay off to consider performance tuning and not wait for the next CPU to arrive. Another thing I would like to point out is all the things that affect performance. Many are focused on the gigahertz rate only, and of course that plays a role. The microprocessor definitely plays a role, and the speed of that microprocessor plays a role. But there's much more to it. For example, what kind of architectural features have been put in to make the processor perform well on certain types of applications? Also, the availability. It's very tempting to wait for the next CPU to arrive, but that could mean a long delay, and I would not recommend doing so. I would look at what's available today, what are the features the processor has, and of course what is the speed. All of these affect performance. But again, there's much more to it than that. You take a CPU, and without anything, the CPU can't do anything. You got to put it into a system. And that's where the configuration of the system starts to matter. For example, how many CPUs do I have? How about my memory? How about my I/O? They all affect performance. In particular, the way the system is connected together. How about the bandwidths in the system? How about the latencies? How about the data bandwidth, address bandwidth? All of these affect performance of an application. On the software side, there are other components that also affect performance. For example, the operating system. Often forgotten, but at the end of the day, the operating system runs our applications. And there could be a lot of opportunity by tuning the operating system by setting environment variables or find some other tunables to make our application run faster. So my strong recommendation is to look into that when you're using your operating system. Try to find out what can help for the performance of the application. Libraries. As another kind of little dark corner of the building, you will get system libraries, but they're not necessarily the best ones for performance. So what I would do is make a study of what kind of libraries are available and what are the best for the performance of my application. Finally, on the software side, there are the compilers. Compilers are fairly complex products. They're powerful tools, and some study of a compiler can be very beneficial. How to use the tool to master the performance of your application. Finally, there's you, the user. The user has a certain expertise in a certain area. You may know the algorithm very well, but maybe you're not a computer scientist. So you don't know the computer all that well. And to a certain extent, that will affect performance, of course. And you may also be short on time. You have a deadline to meet, you have a paper to publish, you have a product to deliver. All of these affect performance. And the bottom line of this slide is, it's just not only raw gigahertz performance. There's much more to it than that. Another thing I would like to point out is the following. Let's say we have a program, and the program runs in 100 seconds. And we have a tool that tells us where we are spending our time. And in this very simple example, I assume I have 4 functions, and 50% of my time is spent in function A, 25% is spent in function B, and 12.5% in C and D. My first question to you could be, what would you consider for tuning if you were to do so? It's kind of staring at you from this slide. Of course, we would start with function A because it's taking half of the time. So if I make A 5 times faster, which is quite a lot, I can look at my program again, the performance of my program, and what I will see is now function B is the most time-consuming part of my program. So the next logical step to take is to optimize program function B. Well, let's say we can make that 5 times faster as well, which is quite an achievement. If we again look at the performance of our application, we see it's dominated by functions C and D that were completely unimportant in the beginning. Now they completely dominate the performance of my application. And as you can imagine, this will never end. The next one to tackle would be C, and after that D, and if there's an E or F, you would just go on. And in a real application, that could be a very, very long and tedious process. So the 2 things to mention here, one of them is that C and D that I haven't optimized completely dominate my performance now. This is generally called Amdahl's law. In a future module, we will investigate this from a parallel point of view, but it's a more general law than just restricted to parallelization. It says the part that you haven't optimized, in my case C and D, will get you sooner than later. Another thing I would like to mention regarding this slide is that what we see is the low-hanging fruit is often in the beginning. It's relatively easy to get a good performance gain by reconsidering the application, maybe play with a few compiler options and choose a different library. That's really the low-hanging fruit and often forgotten. The final thing I would like to say here is that the total speed up is not a factor of 5. Even though we optimized two significant components with a factor of 5, the total speed up is 2.5. Not bad at all, on the contrary, but it's not the factor of 5. And again, that goes back to this Amdahl's law that says that C and D completely dominate my performance now. The next kind of misconception I would like to talk about now is performance as a function of the problem size being solved. That's reflected in this very simple chart. In this chart, I'm showing the expected performance as a function of, let's say, the data set that I'm working on. I could be working on a small data set or a large data set. Many expect to see the same level of performance. Unfortunately, very often this is not the case. Why? The reason is that the underlying memory system is fairly complex. And that's being kind of highlighted and summarized in this slide. On the left-hand side, we see the CPU. The CPU runs at a gigahertz, which is fairly low speed these days. It means it has a clock that ticks at 1 nanosecond. Every 10 to the minus 9 second, this device can produce at least one result for me. The problem is the data that it needs to work on lives in memory. And even the very fast memory that is available today is about 50 times slower than the CPU. That's called a bottleneck. That's a serious bottleneck. And architects know about that. For a long, long time, this has been a known problem. And what they give us is cache memory. Cache memory is nothing more or less than a small buffer memory helps to speed up access to my data. And what I'm showing in this slide is two levels of cache. And the notation is very simple. Level 1 cache is closest to the CPU in terms of access time. I can get my data soonest, quickest from the level 1 cache. Level 2 is further away in time, but it's also bigger. So it's a trade-off size versus speed. And for performance, I really would like to get my data from the cache, not from the memory system. If the CPU needs some data, the hardware will actually work on what's called a cache line. Even if I need a single byte, the hardware will work on what we call a cache line. A cache line is a tiny portion of memory. Could be 32 bytes, 64 bytes, maybe 128. But it's small relative to the total size of the memory and the caches. That byte that I need will be part of a line, and that line will be copied into level 2 cache. From there, it will be copied into the level 1 cache, and now I can access my byte. But all the numbers add up. So this could be a long, long time to get to my data. In the ideal case, the next piece of data could come from the level 1 cache, because that access time is short. That's really the goal of performance tuning. Keep the data close to the CPU for as long as you can. In reality, the situation is much more complex than I just outlined. I will not spend a lot of time on this slide. I just want to show you the complexity of the underlying memory system. So what we have here is the CPU. On the CPU, we'll actually find the registers. The registers are the fastest piece of memory that I have in my system. But they're tiny. It's just a handful of memory that I have. I may have 32 registers, 64, 128, 256. And that's not very much. On the chip, we find specialized caches. There could be a cache for instructions, the I cache. There could be a D cache for data. And there's a fairly obscure cache called TLB. TLB stands for Translation Look-Aside Buffer, and it's really an address cache. It helps speeding up traffic on the address side, so it caches address-related information. In this talk, I will not go into detail, but it does play a fairly important role in performance tuning in general. At a higher level, we'll find a level 2 cache, and in my case, that's a unified cache. What does that mean? That means that both instructions and data will be stored into the unified cache. Then we'll have the physical memory, the RAM, that you're all familiar with. That's order gigabytes, and on some systems even close to a terabyte these days. And then finally we have the virtual memory. Virtual memory is part of my disk. I can declare part of my disk farm to be memory. That's slow, but could be potentially as big as I would like to make it. If the CPU needs some data, it'll first try to access this TLB, which is on the critical path to performance for about any application. The TLB does the address mapping from the virtual address into the physical address, because at the end of the day, my data has to go into the physical memory. That translation is fairly expensive, and it makes sense to cache that mapping information into the TLB. The system works with a page. A page is even bigger than a cache line. A page size is typically 4 kilobyte, 8 kilobyte or more, and that's handled by the operating system. So the system will allocate a whole page, even if I need a byte. The byte that I need will be in that page, and it will be part of a cache line. And again, at the memory level, at the system level, the system works with pages. It doesn't even know about cache lines. And I'll get back to that in a future module, the consequences of that for parallel programming. The line will then be, as I've shown before, will be copied from the memory into the level 2 cache. If it's data, it will go to the data cache that's on the chip, and from there it'll be in the register and the CPU is ready to execute it. And again, that could be a long way. So the goal of performance tuning is to use the data that's closest to the CPU and use it for as long as you can. Hopefully by now it's somewhat clear that the performance line that I was showing a few minutes ago is an ideal world. It's not very likely that you'll see this on a real-world application. On a real-world application, what's more likely to see is that as your data set gets bigger and bigger, the performance drops. And that's kind of summarized in this chart here. As my data set grows and grows, I may not be able to fit my data set in a certain level of the cache, and my performance will take a hit. And things get progressively worse as I move away from the CPU because my data set doesn't fit in the cache anymore. Related to caches and memory, I would like to mention two words: latency and bandwidth. Latency and bandwidth are characteristics of a memory system, or I/O for that matter. Latency is how long it takes to get to the first data element that I need. In a way, that's related to the quality of the wire. If the quality of the wire is very high, the delay is very short and I can get to my first data element very quickly. Bandwidth is related to how many wires I'll be using. I can have many wires and in that way achieve a high bandwidth, getting a lot of data into my CPU. But if the latency is high, it'll still take a long time to get to the first element. If the latency is low, it'll be quick to get to my first element. So bandwidth is about streaming data. And one of the trends that we see in modern processor design is to turn bandwidth into a mechanism that will reduce latency. And I will talk about that later. To demonstrate this kind of behavior, I've taken a very simple program. It computes a polynomial. A vector of inputs is transformed into a vector of outputs doing a polynomial calculation of degree 13. That's a very high degree, and I've taken that because it makes this a CPU-friendly algorithm. With this algorithm, I need one input, in my case called Q of I. That Q of I element is loaded from memory, and then I can do 26 floating point operations on it. When I'm done with those 26 operations, I'll store it back into the memory system, so that's another memory reference. In other words, I have 26 floating point operations and only 2 memory transactions. That's a very CPU-friendly thing to do, and it shows in the performance chart that I'm showing here. What I see is when I make my data set bigger and bigger, I see the classical cache-based behavior. For a while, I get very good performance. That is, if my data fits in the level 1 cache and on this system in the level 2 cache as well, I actually get 99% of the peak performance of this processor. But as soon as the data set is too big and won't fit in the level 2 cache anymore, I'll see a performance drop. On the system that I used for this experiment, it had a level 3 cache, and there we see another performance degradation because my data set is so big, it will not be able to live in a level 3 cache all of the time. Another thing I would like to point out is for a relatively small data set, the CPU does not get up to speed. That's why we see the ramp up of the performance in the first part of this curve. The first part of this curve reflects that the CPU would like to have very long streaming pieces of data to get up to speed. And the fact it doesn't get up to speed yet is because the pieces of data are too short, and that's shown here. Compilers know about that. And what I'm showing you here is what is called code specialization being performed in the Sun Studio compilers. What they do is they decide that to execute a different part of the code if the vector, in this case, is too short. If we wouldn't do that, performance would even be worse than shown here. So we're trying to make the best out of it given the way the hardware is organized. I already mentioned that bandwidth can be turned into a way to reduce latency, and one of the most common ways to do that these days is called Prefetch. It's a memory latency hiding technique. And the way it works is that if you can anticipate what you'll need in the future and have the right hardware support for it, you can speed up your memory access. As I'm trying to show here, let's say I'm summing up elements of a certain data structure. I'm going through a database or some array structure in a scientific program. It doesn't really matter what I'm doing. The key here is that when I access the light green element, I know I'm going to get the bluish element in the future. I just don't need it now, but I know I'll need it in the future. Once I have that knowledge, I can exploit it, again, with the right hardware support. So if I would plot the access time, the access as a function of time, I would have to go to the memory system first, get my first element of data. Once I have that, I can process it. And I'm going to wait for the next piece of data to arrive, and so forth, and so forth. That has a lot of delay. Each time that I go into the memory part, I'll wait for my data to arrive. A better way would be the following. I go to the memory system, get my first piece of data, but while I work on that piece of data, I'm going to prefetch what I need in the future. And then by the time that I need it, it's either already in my memory system, in my registers or in my level 1 cache, or it's on its way to me. And effectively, I reduce the wait time to get to my data. This is called prefetch, and it's a very important component in performance on modern systems. To illustrate this, I took my same little test program and I recompiled with this prefetch mechanism enabled. And that's the red curve shown in this chart. And what we see, the system is able to completely hide the latency to the level 3 cache. As long as I stay within the level 3 cache, there's no performance degradation anymore. The red curve is higher than the blue one. Only when my dataset exceeds the size of the level 3 cache, I see some degradation. But it's certainly much, much better than what I had before. And altogether I get about 2.5x performance increase, which is really very nice. And again, it's just to illustrate the importance of prefetch as a technique to deal with relatively slow memory subsystems. To summarize, there are 5 different ways to optimize an application, and I strongly recommend to go through all of them. First, look into your operating system. Whatever you use, it may have features that are beneficial to performance that are not enabled by default. Often enabling them is not hard, you just need to know about them. Next, look at the libraries that you're using. There could be faster versions of libraries out there available to you. And also there, using them often involves a very small effort, so not much work and another performance gain. Compilers that translate your program, yes, they play an important role, and I certainly would like to encourage you to read a little on the compiler that you're using to find out what kind of options are beneficial for performance. Number 4 is source code changes. Personally, I'm very reluctant to make them because compilers these days are very powerful, they can do a lot for you, but sometimes a little rewrite where the compiler lacks the knowledge that you have can be beneficial. Number 5 is parallelization, and that's of course the theme of this whole programming series. And the effort there could be anything between very trivial and substantial. And that's what we're going to talk about in the remainder of this series. And I hope you'll all stay tuned. Thank you for watching. Please look for Module 2, where we delve into multi-core processor architectures. For more information on how Sun can help you designing parallel applications, please go to the URL listed on the screen here or send an email to the email address, and we welcome your feedback. Thank you.